Hello there! Welcome to the second knowledge clip for the section of Thermodynamics of Physical Chemistry of the Life Sciences. The menu for today's knowledge clip is composed of two parts. The first part deals with how the so-called Gibbs free energy serves as a measure of the maximum non-volume work. The second part describes how the Gibbs free energy can additionally serve as a measure whether a process is spontaneously or not. So let's get started. Okay, so let's begin with the first part. The Gibbs free energy as a measure of the maximum non-volume work a system can perform. Remember from the last knowledge clip, non-volume work is very important for many biological processes. The definition of the Gibbs free energy is actually quite similar to the definition of the entropy, as we will see in the following. Let's begin our analysis of the maximum non-volume work for the Gibbs free energy by taking a look at the internal energy U. So, to calculate a change of the internal energy U, du, we simply use the first law of thermodynamics, which states that the U is given by the amount of heat being added or taken out of the system plus the amount of work that the system performs on the surrounding or that the surrounding performs on the system. Right? So let's consider a system that only does volume work for now. Then we express dV with minus pdV, as we have done before. So with this equation, we can now see that for a constant volume, which we indicate here with the index, the meaning of the internal energy change, du, is simply the amount of heat that flows. Because when the volume is constant, then dV here is 0, and this entire term is 0, and only dq stays. Okay, so the meaning of an internal energy change at constant volume is the amount of heat that flows. Good. The enthalpy, H. The definition of the enthalpy, H, is U plus PV. Right? It's simply a definition that was man-made for giving the enthalpy certain features that allow us to interpret it, for instance, for the heat transfer, as we will see in a moment. Okay, so to calculate a change of the enthalpy H, dH, we apply the infinitesimal on U and PV, so du plus dPV, and dPV can be expressed with the product rule via PdV plus VdP, right? Okay, so now we can express du with the first law of thermodynamics, dq minus pdV, which I'm doing here, right? So simply I substituted this in for du, and then the remaining terms, pdV plus vdp. Aha! Now we can see that this minus pdV term and this plus pdV term, they cancel out, and we simply have only left dq plus vdp. Okay, now we can state that an infinitesimal small change of the enthalpy, dH, at constant pressure is equal to the amount of heat that flows. Because, again, the dP term is 0 when the pressure is constant, and only the dq term is there. So this is really useful because in biological systems, often the pressure is constant, and then we can actually measure with a so-called calorimeter the enthalpy change of the system by measuring the heat flow, which we can measure with this calorimeter. So the definition of the enthalpy allows us to relate measurable quantities, which are for instance heat flow, to enthalpy changes of the system. Good. Okay. So let's talk about non-volume work, which I abbreviate now as W prime. An example for non-volume work is electrical work. It's all types of work that do not involve PV. They are designated as non-volume work. Okay? So the first law of thermodynamics, as we have already seen, says that du, the internal energy, changes by heat addition plus work change. And this work change we now express both with volume work and non-volume work. Yeah? So the heat term dq, we can substitute that with TdS, temperature times entropy change, which we have introduced this equation earlier. And then here I just keep the PDV and the non-volume work terms in this equation. Okay, now what we see is something what the meaning of the internal energy can be also interpreted, but this time not at constant volume as before, but at constant entropy and also constant volume. We can say that a change of the internal energy corresponds to the amount of non-volume work that is performed, since ds will be 0 for constant entropy and dV is also 0 for constant volume, right? So the internal energy change can serve as a measure of the amount of non-volume work if the entropy and the volume are constant. However, practically that is not very useful, because in many processes the entropy is actually changing, right? Most of the time the system will have a change in the entropy, right? There's more disorder often generated, so the entropy is not constant. So internal energy is not suitable really to measure the amount of non-volume work that can be performed, right? And that non-volume work is so important because it tells us about, for instance, how this kinesin motor protein walks on a microtubule, right? So that's why we need to search for a different way to express the amount of non-volume work. Let's see if maybe the enthalpy works better. dH, an infinitesimal small change of the enthalpy. Okay, we already know the definition of H is U plus PV, so we apply the infinitesimal on that, and then we just write again du plus PdV plus VdP in the same way that we have done before up here, right? Okay, and again we can now replace du simply with what we previously obtained here, TdS minus PDV plus the change or the amount of non-volume work, dV prime. Okay, the remaining two terms here, of course, we shouldn't forget them, plus PDV plus VdP. And what do we see? Let's take a look. I'm going to see that this part here and that part, again, they cancel each other out. Okay, and then all that is left is TdS plus VdP plus the amount of non-volume work. Okay, now we see a change in enthalpy at constant entropy and constant pressure, which means ds is 0 and dP is 0, corresponds to the amount of non-volume work that a system can perform. Again, same problem like we had before. The non-volume work it's not very suitable to look at the enthalpy change to express it, because in most processes the entropy will change. So we need a different definition to express the maximum amount of non-volume work. Both internal energy and enthalpy are not suitable because they require the entropy to remain constant, which is not suitable. Good. So that's the moment now where we introduce the Gibbs free energy, G. It's like enthalpy is defined as H, Gibbs free energy we define as G. And G, just like the enthalpy, we just write a definition, and in this example it is the enthalpy H minus the temperature times the entropy. Right? That's the formula that defines the Gibbs free energy. Okay, so following this logic that we have done already for the change of the internal energy and the change of the enthalpy, we can now do the same steps for a change of the Gibbs free energy. What would that be? dG is dH, right? Change in enthalpy minus TdS minus SdT. Again, the product rule applied to this TS term gives these two terms. Yeah, we can continue by defining dH, or by using the definition for dH, which we have already obtained over here, TdS plus VdP plus dW prime, right? Which is up here. So we just plug that in, and the remaining two terms, minus TdS minus SdT, oh, here's underlined, these two are corresponding, minus TdS minus SdT are of course also to be considered. Okay, let's take a look which terms stay. I see here there's a minus TdS, a plus TdS, and here's a minus TdS. So these two go away. Now there's no more entropy change there to express an Gibbs free energy change. Nice. Let's see what that leads to. It just leads to minus SdT plus VdP plus the change or the non-volume work here, right? Okay, now we see an infinite or a change of the Gibbs free energy at constant pressure and constant temperature, right? Constant pressure means that VdP will be 0. Constant temperature means that minus SdT will be 0. That change of Gibbs free energy simply corresponds to the amount of non-volume work. And you now see how useful this Gibbs free energy concept is. Because in many biological processes, the pressure as well as the temperature remain constant. And then we can actually use the change of the Gibbs free energy to learn about how much non-volume work can be performed by the system, as you have seen, which is so relevant for the biochemical processes inside of a cell. Excellent. So when we integrate dG at constant pressure and temperature, we simply obtain the maximum amount of non-volume work that a system can perform, which, as I mentioned, is essential in biology. So, summarizing this section, a change of the Gibbs free energy at constant pressure and temperature gives you the maximum amount of work that can be performed, of non-volume work, pardon. So, the second part now of this knowledge clip, we're going to talk about how the Gibbs free energy has a second meaning, which is a measure whether a process is spontaneous or not. Let's get started. Okay, let's get started. So I'm drawing here a large reservoir. That reservoir is our environment, for instance, here. It's the atmosphere of planet Earth, for instance. It has a certain pressure and a certain temperature. And inside of the reservoir, there is the system. I depict the system just as a model here as this cylinder piston. That piston is frictionless, so it can move up or down. And what that does basically is it allows the system to stay at a constant pressure, P, which is the same as the pressure of the surrounding. Good. Furthermore, that system is also able to exchange heat with the surrounding via the walls of the container. So Either when there is heat generated in the system, it can flow to the surrounding, or when the system wants to absorb heat, the surrounding can supply the heat. But because the surrounding, the reservoir, is so huge compared to the system, its temperature is not going to change if there is any heat flow, because it's so big that any small amount of heat that is being taken from the reservoir is not going to change the temperature of the reservoir. So the temperature of the reservoir will stay constant, and because that temperature is now going to be the same that you have in the temperature due to the heat exchange, you will always have the same temperature in the system as you have in the surroundings, right? Okay, so now let's take a look at the enthalpy change of that system, dH. Right? We've already derived an expression for that. It's the amount of heat that flows plus the VdP term plus the non-volume work term. Okay, but we look here at a system that has a constant pressure, P, because of the piston that can move up or down. Right? P is constant. So if P is constant, dP is 0, and this whole term will be 0. And let's additionally assume that there's no non-volume work performed by the system. Okay, and under these circumstances, we can say that the enthalpy change of the system at constant pressure and no non-volume work simply corresponds to the amount of heat that crosses the system's boundary. So you can just say that dQ will be dH here, right? Based on the definition of the entropy, ds, we can now rewrite dQ with T times ds, right? So with that, I can rearrange the right and that term, enthalpy change, to obtain the entropy change of the system at constant pressure is simply the enthalpy change divided by the temperature, T. Now we have an expression that tells us how much the entropy of the system will change. We will use this expression in the next steps. Let's first take a look at the second law of thermodynamics. That law, the second, states that for a spontaneous process, the entropy change of the universe will always be larger than 0. Well, that's a fundamental fact. Any spontaneous process that happens comes with an increase of the entropy. The multiplicity will always increase, right? The universe will always strive towards states of more disorder or higher multiplicity, simply. That's just a statistical fact, and we express it here in calorimetric, in thermodynamic quantities. Okay, so what does that mean, the entropy of the universe increases? It means that the sum of the entropy change of the system plus the entropy change of the reservoir, these two together will increase. And for this example here, the reservoir, let's say it could represent our whole, it's representing our whole universe. And the universe itself, because of the first law of thermodynamics, it's not changing its internal energy. Energy is preserved, right? U is constant. And supposedly also the volume of the universe, V, is not changing. It's constant, right? And let's additionally say that there's no non-volume work performed for this second law to be true in this way. So, second law says that the entropy of the universe always increases, which is the sum of the entropy change of the system plus the entropy change of the reservoir. Okay, so, but there's a problem with this equation, namely that we would like to describe everything from the perspective of the system, because the system, we know what it is made of. The reservoir is made of a lot of different things, and it's very big, and it's too complicated to be described in detail with equations. So it's better to express the change of the entropy of the universe with the system alone. That's what I would like to do in the next step, to express the change of the entropy of the universe only from the perspective of the system. Yeah? So that means we need to get rid of this entropy change of the reservoir term. How can we do that? Let's think of how we can express the entropy change of the reservoir. We're going to use this equation that we derived before, which states that the entropy change at constant pressure, which is the case for the reservoir, corresponds to the enthalpy change at constant temperature. Okay, we just write that. The enthalpy change of the reservoir divided by the temperature. Okay, now what is that enthalpy change of the reservoir? Let's think about it. We know that the enthalpy change corresponds to the heat that is exchanged across the system's boundary. When the system now gives heat to the reservoir, that basically means that exactly the same amount of heat will arrive in the reservoir. No? The amount of heat that goes out of the system, if it goes out, right, the system will have a negative heat, but then that heat will be added to the reservoir. So the heat that's added to the reservoir is going to be positive, right? This is for constant pressure, everything, of course. So the heat that goes into the reservoir is the negative of the heat that comes from the system, right? And since we know that the heat corresponds to the enthalpy change, we can rewrite this at the constant pressure as that the enthalpy change of the reservoir simply is the negative enthalpy change of the system. Aha! And now you can already see we have here a way to express the entropy change of the reservoir with the enthalpy change of the system, which we do next. Oh, I rearrange everything a little. So now I write the entropy change of the reservoir is simply given by the negative enthalpy change of the system divided by the temperature, right? Okay, and with this we now have an expression, or like a way to replace the entropy change of the reservoir. So I just write now the universe entropy change is the system's entropy change minus the enthalpy change of the system divided by the temperature. And second law says that the entropy change of the universe must always be larger. And we can now calculate that just with system parameters. Excellent. So now I multiply with negative t. So minus TdS of the universe is then dH system, which now is positive, minus TdS system. And because I multiplied with minus, now translating the second law of thermodynamics, this expression minus TdS universe must actually be smaller than 0, right? See, basically the opposite of what we had here due to the multiplication with minus t. So this minus TdS universe we say is the change of the Gibbs free energy at constant temperature and pressure, minus TdS universe. And minus TdS universe means dH system minus TdS system at constant temperature and pressure. And for a spontaneous process, it must be smaller than 0. To summarize, for a spontaneous process, the change of the Gibbs free energy at constant temperature and pressure will always be smaller than 0. The Gibbs free energy change is simply a different way of expressing the second law of thermodynamics, which says that the entropy of the universe increases. Just for the Gibbs free energy, it must decrease, right? So this is very useful to understand many processes of biological relevance. For instance, the energy that can be extracted from a concentrated region of molecules that then over time diffuse and mix with their surroundings, which gives you an amount of non-volume work that can, for instance, be used to synthesize ATP, a molecule of high relevance for many biological processes. Moreover, the hydrolysis of ATP itself, which for instance drives the movement of the motor protein kinesin that travels through the cell and transports, like a delivery truck, vesicles filled with useful stuff inside along microtubules. This hydrolysis reaction of ATP is also a spontaneous process. It comes also with a negative Gibbs free energy. You can see the Gibbs free energy change or definition is very important for many biological processes. With this, thank you for your attention.